All right, everybody, it's just about time. That clock is a little bit off. I'm going to go ahead and get started. Hello and welcome, everybody. I am Dr. Annan, and I have taught this class like 40 times. I can still hear myself giving this lecture 6 months ago in my head. I do it all the time. It's my favorite class to teach, and you'll find out why pretty quickly. I really, really enjoy differential equations and linear algebra, and I literally wrote the book on it. Right here. I hope that you all have a copy. If by any chance you don't, I've got extra copies in my office, and there's a big study space outside of my office. You're certainly welcome to hang out down there. You don't have to bring the book all the time to campus because I've got extra copies you can use if you're doing some work down there. Anyway, I want to thank you for bearing with me last week. One of the things about myself that's a little different, maybe not expected out of a math professor, is I'm really big into mountaineering. I've climbed mountains all over the world, snow volcanoes up to technical rock climbing stuff. It turns out the latter part of the summer is a really good time to do some of those kind of things. And I have a summer place out in the mountains, in the Rocky Mountains. And I was finishing up an adventure out there, and then I drove back just a few days ago. So it looks like I missed out on some of the heat, but not all of it. It's still pretty hot here. So whereas where I spend my time up in the mountains is usually very, very cold. So I have to get used to this change of climate. But anyway, I do appreciate you bearing with me. I saw all of the notes that you took on those videos from last week. Thank you for doing that. Of course, if you have some questions about any of that material, you're welcome to ask me. And I will always start class with kind of a recap, or what I would call like a summary of really the big main takeaway points from the previous class. So in this case, the previous class would have been all of those videos that you watched. And so this would be it. And if you just want to take a picture of it with your phone, or if you just want to write it all down, it's great. But what students generally will tell you about halfway through the semester is that they wish that they would have been writing them down all along, because it's really a good way to get the key points out of what you're supposed to know up to this point. Okay, now that we are back in person and we're going to actually have a traditional class here today, I want to get a sense of the attendance and the enrollment and all of that, because I do know there's some people waiting to try to get into the class. So I printed out my roster as of like a few hours ago this morning. And what this is the current enrolled students. So I'm going to send this around and ask you to just take a pencil. And in that first column, there's a little place to do a little checkbox. Column says select on the top of it. If you could just check off next to your name, that way I'll know that you're here. If you're not on this list, but you're trying to get into the class, it probably means you're not enrolled yet. And what I'd like you to do if you're not enrolled and you're trying to get in is to just on the second page on the bottom, just add your name there for me. And once this goes all the way around the room and I get everybody checked in, I'm going to actually read through the names a little bit and see where we're at. Ordinarily, like, I love teaching. I love it. The more people I can help, the better. And I would take everybody into the class. The only problem is that the fire marshal will not take everybody. If I tell the math department I want to add all these extra people to my roster, they will reject that and say, oh, the classroom that you're in only takes this many people. So I have to kind of check my numbers on this. And there might be some people, I mean, it looks like there's a couple empty seats, at least for the moment. There might be some people on my enrolled roster who are not here, and I might be able to make room for somebody who's waiting. So let's just check that out. Let me have you go around and just check off your name on that. It should be alphabetical by last name, and then add your name if it's not already on there. Okay, so that was the first thing. The second thing I wanted to mention is there's a lot of work in this class. You will get your money's worth in terms of the workload, and that includes especially homework assignments. However, one thing I will do, first of all, I'll explain in a little while. I'm going to be dropping your 2 lowest homework assignments. So if you get into a pinch at some point, just can't get one done or something, it's probably not going to ruin your whole semester. But the other thing is I will not always succeed, but I will try as much as I can to help you with the homework even during class. So you might have noticed on the syllabus, the homework is never due until 11:59 on whatever day it is. So there is homework due tonight by the end of the evening, 11:59. However, I am willing to help you with some of the problems. I did that for my morning class and I'm gonna do it again for you guys. So whenever we come in, you'll notice on the sideboard over here, I'll tend to write down the sections that the homework is covering. And what you can do is if there was something you were stuck on, a particular problem that you hope that I can take the time. I don't promise I always have time, but I'll try to take the time to help. You can write those problem numbers down on the board over here. Now, nobody's put anything down there so far because obviously you may not have known what it was there for. That's okay because what I will always do also in this class is take a 10-minute break. So in the middle of the class today, we'll take 10 minutes and let everybody kind of stretch their legs or whatever. And if at that point you get organized and want to put something on the board over here, you're welcome to do that. And in the second half of our class, I will try to answer some of those homework questions. If I'm not able to answer all of them, or if you still have further questions, of course, you probably know that I have a lot of office hours. I do have another class right after this one, so I can't like do a bunch of office hours immediately after the class is over. But this evening, once my second class is over at 5:15, I'll be going to my office and from 5:30 to 7, I think, and then from 8:30 to 10, pretty much for 3 hours on Tuesday nights, I will have office hours before the home, because you usually will have a Tuesday assignment. So I'm trying to be around a lot on Tuesdays. You don't have to come in person. You have my Zoom information in the syllabus, so you can come to my office hours in Zoom, but you can come in person. My office is down in the basement of the building, way down on the bottom floor. So feel free to drop in there. There's a study room outside my office, as I mentioned, and you can hang out there and get some work done and talk to me if you have questions. Okay, so that's what I would suggest about that. Okay. Anybody have any questions about anything from either the syllabus, anything I've said so far today, or just in general, kind of how things are going to run? Or about the math, actually, that you took video notes on last week. Does everybody feel pretty reasonable about that so far? Well, we're going to review it a little bit today. So you're going to see that because, of course, this material tends to build on itself, which means that you can't get away with not learning something along the way because you're going to need it for the next thing. And that is certainly true in today's lecture. So let me start by doing a quick review, maybe not of everything from all of the videos that you watched last week, but some of the highlights I have put into this nice little sort of cheat sheet here that we can kind of pay attention to. Anytime you see something in a box, I probably should have a box on this as well, and maybe even this. Anytime I put something in a box on the board, it's definitely something you will want to be getting good notes on and make sure that you're learning it. Students will always ask me, oh, can we have a cheat sheet for all of this stuff? My answer is no. I want you to actually really learn these equations. And actually, in the long run, it's to your benefit because I can give you partial credit on an exam, let's say, for knowing what Newton's law of cooling is or what the equation for a linear differential equation is, right? If I give you all these formulas as a handout, then I'm not going to be giving you points for them. And instead, then you're going to be graded on everything else, which, you know, I think it'd be nice to get some free points on some of this stuff. So I will be expecting you to learn all of the formulas. No cheat sheets, I'm a very theoretical guy. I kind of do. I tell people when I go mountaineering that I can go to the top of this mountain with a pencil and a paper and do all of my work that I do as a mathematician up there. I don't need a computer. I don't need a calculator. I can just kind of do it freehand, pencil and paper only. So you'll see that a little bit as we go on. Okay. Anyway, yeah, so this is a nice summary. In the videos that you guys watched last week, you should have been learning about separable and linear differential equations. And these are the two most common types of differential equations out there. So if we know how to solve these equations, we're already well on our way to being able to solve a number of scientific and engineering related problems. So this is a good news, right? I've even got a couple of applications that you watched videos about. The Newton's law of cooling differential equation. This one was separable. And then the mixing problems differential equation, which was linear. So I gave a couple of examples, just easy examples of those applications. But just to review again, the separable differential equations, those are the ones where you can get the x's and y's that show up in the equation onto opposite sides of the equal sign. Now, it may not be presented to you that way in the first place, so it might be important for you to algebraically manipulate the expression in order to achieve that. But it is, if it's a separable differential equation, it should be achievable to get the variables onto separate sides of the equal sign. It really is, the name of the equation really is telling, right? It's really what you want to keep in mind. Once you have it separated, which might already have taken you a little bit of work, then you can actually, the method for actually solving this equation is to integrate on both sides, right? So you do an integral on the left, you do an integral on the right. And if possible, you can then isolate the y and solve for the y explicitly. And that's not always possible. There are, certain equations that have to be represented implicitly. But the preference would be to try to give an explicit solution for y, if possible, right? Okay, so I do want to point out, obviously, you need to be able to do some basic calculus around here. Integrals being first and foremost, you're already seeing that. Derivatives, of course, will show up quite a bit. However, I'm not, again, when I go about writing my exams and so on, it's not my goal to come up with problems that throw people off because of things that are not to do with this class at all. Like, so I'm not going to be trying my best to come up with the hardest possible limits, right? I'm going to be trying to give you things where you can demonstrate the material from this class. Okay, so I think everybody in here should be able to do U substitutions for integration. And maybe on an occasion, you're going to see integration by parts, those two. Beyond that, I really don't feel good about, asking students to remember all, because you learned like 6 or 7 different integration techniques. I'm probably not going to give you a huge workout on all of those types of integration techniques. I really want to see, well, can you identify a separable differential equation? Can you get it separated? Do you know what the method is generally, right? And I don't want to get hung up on the other stuff too. And if you did make a mistake with an integral or a derivative somewhere, I try not to be too harsh on that because it's not really what this class is about, right? But technically, it's a prerequisite. You've got to be able to do some integrals as well. Newton's law of cooling is an application of separable differential equations. Maybe just on the side here, I should have written down, when you solve Newton's law of cooling, and I did this last week in the videos that you watched, you solve for the temperature of an object as a function of time. And this is the general solution to it. So this is the differential equation. This has the derivative of the temperature in it. This is actually the solution to it. Don't get them confused. I put this question on my final exam just last semester. I said, write down the differential equation for Newton's law of cooling. And a bunch of people wrote this down. This is not a differential equation. This is actually the solution to the differential equation. So, but anyway, I won't review that right now. This was certainly something that was in the videos that you watched last week. But it's nice to have an application of separable differential equations. The other one that you've already taken a look at, I hope, are the linear differential equations. Here's the form that a linear differential equation should look like. And again, you might have to manipulate it into that form if it's not presented that way in the first place. So sometimes there's a little bit of a work that has to go into it ahead of time. But you have y prime plus p of x times y equals q of x. And what we learned in the videos is that those can be solved by using the integrating factor technique. And I derived that in the lecture that you watched. Basically, I, which is the integrating factor, is e raised to the power of the integral of p of x dx. You will want to memorize that, right? So the p of x is the expression in front of the y right here. Yeah. And so the integrating factor is e to that integral. So again, you're doing integration to do this method. Once you work out the integrating factor, then a bunch of magic happens, and I showed it in the video that you watched. But the magic is that you can then take your original differential equation and turn it into the derivative of a product, right? And once you've got it in this form, so notice that the q of x, which was on the right-hand side, picks up a factor of I as well. Once you've got it into this form, my friends, you can now solve for y, right? You just integrate both sides and isolate the y from there. Yeah, that's how it works. And I did some examples that you would have taken some notes on. And we're going to practice this method. We're going to practice both of these again today. So if in case you're a little rusty on it, don't worry, you'll see it again today. I'm probably not going to do the mixing problems today. There are a couple of homework problems for Thursday, the next assignment, where you're going to be looking at this differential equation for mixing problems. And so maybe on Thursday, if we talk about that, I'll remind you about what all these variables mean. For the time being, I just wanted to kind of flash it in front of you again and make sure that you have that in your notes at some point. Okay. Does anyone have any questions about any of that so far? Are so good? I love questions, by the way, so I hope you won't hesitate to ask. Actually, I get really excited about what I'm talking about usually. Like, I really love this stuff. And so what happens though is and I don't mean to do this, but I start going really fast. I get really enthusiastic. So what you have to do is ask me a question and that'll sort of calm me down a little bit. And I'll go a little bit slower and try to make sure I'm not going too haywire about things. All right. By the way, I'm also recording this. I'm recording myself so that I can post this up later onto my YouTube. Have you all become YouTube subscribers yet? Yes, I hope. I'm trying to. Anyway, I have a lot of videos up there, and I'll be putting these class lectures up. Let's say in 2 or 3 weeks, you're like, gee, I don't think I remember much about linear differential equations. Well, you'll be able to rewatch a portion or all of whatever you want to. I'll be trying to get these recorded throughout the semester, just for you guys to take advantage of. Okay. No questions then on anything related to the recall over here. Yes, please.
So for the method, for both separable and linear,
Yeah.
we're still integrating and solving for y. It's just we're using the integrating factor.
Yeah, exactly. The goal is ultimately to solve for y, if possible. And in the second case, it's a little bit of an extra step because you actually have to do 2 integrals. You have to integrate to find what I is, and then you actually have to do an integral down here when you're trying to isolate the y as well. But both methods do involve integration. Yeah, good question. Everybody else okay so far? Well, you know what, guys? I could spend, I mean, these are not the only 2 types of differential equations. So I could present a 3rd one, and a 4th one, and a 5th one, and a 6th one, and I could go on and literally I could fill 15 weeks this way. I could do that, and we would have so many things to memorize. And it would be pretty boring after a while. It would be fairly monotonous. It'd be like, God, he's going to show us another differential equation I don't want to see anymore, right? So I'm not going to do that because I don't think that's terribly instructive. If you're really into this stuff in the future, you'll be able to read about other types of differential equations. Instead, what I'm going to do is I'm going to spend a little bit of half of a lecture today talking about a technique or a tool that can be used really in any situation to maybe help us solve a differential equation. Maybe there's a differential equation that we do not yet know how to solve. But if we apply this tool that I'm about to explain, we can convert it into something that we already know how to solve. Now that's kind of more of a conceptual strategy type of approach that I think could be very useful for people to learn. And the name of this technique, and it's covered in the next section in the book, this is what we're going to look at today, section 1.8. The name of this technique, guys, it is simply something called change of variables. Right, change of variables. So I'm going to illustrate this method using two examples. I'll call them A and B right here in my notes. And the first one is something called a Bernoulli differential equation, named after a fairly famous mathematician. And then the second one goes under the name homogeneous differential equation of degree 0. Okay. And again, I'm not trying to just add to the laundry list of types of differential equations. This is more about learning what the technique has, as what the power of this technique is, change of variables. Basically, what we're going to do, guys, is we're going to take our Bernoulli differential equation, which at this moment we don't know how to solve. We haven't learned this yet, but we're going to convert it to a linear one. Right? That's going to be the idea. And then we're going to take the homogeneous differential equations of degree 0, and we're going to learn how to always convert those into a separable one. Now, guys, this is a strategy that mathematicians use a lot. Take a problem that you don't know how to solve and figure out how to convert it into one that you already know how to solve. You even do that in calculus. Like if you have an integral that you don't know how to do, you can try a U substitution, which is really a change of variables that converts your hard integral into something that then suddenly you are able to do the antiderivative for. So that it's not that bizarre of an idea. And I'd like to share this idea with you here in the context of these differential equations. So let's start with part A. And I'm going to, anytime I make a new definition, I'll use DEFN to abbreviate this. And I'm going to give you the definition right now of a Bernoulli differential equation. So we'll start with that. A Bernoulli differential equation has the form, and here it is, y prime plus p of x times y equals, now so far it looks exactly the same on the left as the linear differential equation, but on the right side it's slightly different. It's q of x times y to the n. All right, y to the n, that power of y is what's making it not linear anymore, right? I think I talked about this in the videos. You can't have a linear equation that has a y squared in it, or a y cubed, or a square root of y, or anything like that. The only power of y that you're allowed to have in a linear differential equation is the first power of y. So this is no longer linear, but it's awfully close. It's awfully close. There's just this y to the n on the right-hand side. Okay, so you're going to need to know this. This is the form of a Bernoulli differential equation. And to solve it, we are going to change the variables in such a manner that this gets converted into a linear differential equation. So let's write that down. To solve this, can you guys see me coming in here on Thursday? And we'll have a third line over here where we have Bernoulli differential equation. We write down the form of it. Then the method is what I'm about to explain, and so on and so forth, right? So it makes sense to kind of just build off of what we've already started developing here. So we use a change of variables, and I'm going to go ahead and I guess I'll come over here to write down the rest of this. I'm going to use the same old U that you use in the context of U substitutions. So I'll write it as U equals, and here it is, y to the power of 1 minus n. Now, I assure you that I did not come up with that. This change of variables was discovered way before I was around, and certainly by somebody a whole lot smarter than me, figured out that this change of variables is what we need to use. And so we're going to use it because what will happen is this converts the differential equation into, and if you don't mind in your notes, put a little asterisk next to the word into there, and I'm gonna explain in a minute what's gonna go below that. But it turns it into a new differential equation. Let me write it down here. U prime plus 1 minus n times p of x times u equals 1 minus n times q of x. So there it is. Now, I am normally not that professor who just sort of hands you equations without any proof or justification or whatever. I tend to like to explain all of it. Once in a while, it's such a tangential thing and it's just not really worth doing that. And here's where I'm putting this asterisk. There is a video where I actually show how the conversion works. Now, this is not required. You don't have to watch it. This is for the students out there who really don't really want to just take this on faith at face value. They want to see where it's coming from. But it gives me a chance, and I've got my screen down for a reason over here, guys, on the far right of our front board. It gives me a reason to show you in the Canvas learning system. There is a link over here on the left that says Pages. Pages is where I put all of my videos. For some reason, Canvas won't let me put them anywhere else. So I put them in the Pages section. And right at the top, there is a link that says Additional Videos. So if we click on this, all of you who have become used to subscribers of mine already know this. I have a ton of videos up here. There is a video, the one that is right here next to my cursor, that says converting a Bernoulli differential equation to a linear differential equation. It's 3 minutes long. It's not very long. But if you're interested in seeing the derivation, you could certainly take a look at that and fill in the details. But I'm going to skip that and just ask you to see the video for it. Okay? Now, guys, this n that is messing everything up on the right-hand side is a number. It is just some specific number. So if I look at this differential equation that supposedly my video explains where it came from, if I look at that, the n is just a number. So 1 minus n is just a number being attached to the p of x, right? So this is still kind of u prime plus some function of x times u. And on the other side of the equal sign, what we have is a number times the original q of x. So again, the main thing that has happened though is that on the right-hand side, there is no u to the n. Like we started with a y to the n. When we did this conversion process, in the derivation that you'll see in this video, if you watch it, you'll see that you don't have the u anywhere on the right-hand side. And what that means, my friends, is that this one, this is linear. This is now linear. This becomes linear. That is the point. That is the point. So we have converted a Bernoulli differential equation into a linear one. All right. Everybody feeling all right so far? Let's do an example to practice this. And make sure everybody follows along on this and let me know if there's any questions as we do it. So I'm going to do a quick example on this board here. And here it is. I'd like to solve y prime plus 2x all divided by 1 plus x squared times y equals xy squared. There it is. This is the one I want to solve. You can kind of tell, looking at this, that the p of x is right here. The q of x is just the x. And it's because of the y squared that this is not linear, right? We're not allowed to have y squared in a linear equation. So this is not linear, and it is exactly in this form of a Bernoulli equation, right? So just to get you some good habits going, because I like to give people partial credit for everything they know on every exam or whatever that we do. I would start off by telling everybody that you know that it's Bernoulli. And a really good thing to add while you're at it is, what is the n value? What is the n value here? 2, right? Just the power of y that we see. So this is Bernoulli with n equals 2. If you write that down, I can give you points for knowing that. By the way, I always ask these. I like the Bernoulli equations because they illustrate this powerful technique. And once you end up with your linear differential equation, then you get to show me that you can solve a linear differential equation, which is really important to be able to do as well. Nobody gets out of a 250B class without knowing how to solve a linear differential equation. So for sure, this is the type of problem that I like. Bernoulli with n equals 2. The next thing I like to do is write down what my change of variables would be, right? We've got the boxed equation there, u equals y to the 1 minus n. And now that I have n, I'll just go ahead and put it in there. So y to the 1 minus 2. If I take a -1 power of something, that's really just the same as a reciprocal. So I could write it as 1 over y. So the u is just 1 over y. They are reciprocals of each other. Okay, and then I'm going to go ahead. I think I can squeeze it right here. I'm going to write down the new differential equation. And this one will be the one that has become linear then. I'm going to write down this new differential equation based on what's in the box right here. Okay, so I start off with u prime. And then notice we have 1 minus n. If n is 2, then 1 minus n is actually a -1. That's just really a sign change on whatever the p of x was. So instead of plus, I now have minus 2x divided by 1 plus x squared times u. And then on the other side of the equation, we take the q of x and multiply it by 1 minus n. Again, 1 minus 2 is just -1. So it becomes negative of whatever q of x was. The q of x was just x. Okay, so this is our new linear differential equation. So Bernoulli equations always become linear through this process, right? And once we have the linear differential equation, then we're going to use our method here with the integrating factor, right, that we've learned in last week's videos. We're going to use that to now solve this equation. So this is a good chance to review that as well. Am I going too fast? Any questions so far? Okay, let's try. Let's see if we can solve this one now using the integrating factor. So once we have a linear equation, we have to use integrating factors to solve it. And I like to use an I for that. And remember that the integrating factor is e raised to the power of the integral of p of x dx, but I want to caution you that we're now talking about the new p of x, not the p of x from the original problem that I had identified earlier. This is now the differential equation that I'm playing with. And so I've got to identify my p of x off of this. And in particular, the key thing is there's a minus sign. That minus is part of the p of x. So I'm going to put that in here. In fact, I'll put it outside the integral. So minus the integral of, what is that? 2x over 1 plus x squared dx. Yeah. A common mistake is to not include the negative. But this is a minus, and that is part of the p of x here. So we got to make sure we write that down. Okay. Got to do this integral here. So this is e to the negative. Does anybody have an idea for doing that integration? Yeah, I would use u substitution, right? If you notice the denominator is 1 plus x squared, well, the derivative of that is exactly the numerator, which is the 2x. So this is really the integral of du over u. What is the antiderivative of 1 over u du? The natural log, very good. We have the natural log of the absolute value of whatever u was. In this case, it's 1 plus x squared. Okay. Well, when I do those kind of antiderivatives, normally I have to add a plus C. Your calculus teachers would have harped over and over and over again about that. At least if I was your calculus teacher, I would have. Do I need the plus C here? If you've watched my videos, you know that you don't, right? It's because we only need one acceptable antiderivative. We don't have to find all possible families of antiderivatives here, just one. And why not make it easy? Add nothing as your constant on the end of that. So just leave that off. No need for a plus C here. The other thing is, do we really need the absolute value bars here? Well, last time I checked, x squared plus 1 is always positive, and taking absolute value of that does nothing. It's really not necessary. So I don't even need that. Maybe let's just take an intermediate step and just get rid of the absolute value bar. So I'll just write it as, I mean, it wouldn't be wrong to have it, but I'm just going to leave it without absolute value bars there. Now, my dream step here is to cancel the e with the ln because they are inverse functions. But we always have to be a little careful, and this came up in the examples last week as well. When you have some coefficient here in front of the logarithm, you can't just bypass it and cancel the exponential and the logarithm. Instead, you have to use this, what is it, a property of logarithms that says that this coefficient can be put upstairs as an exponent of whatever's the inside the logarithm function. So actually, this is a -1 exponent. Let's just write it here. 1 plus x squared to the -1. And then I can cancel the e with the ln for sure, right? And just to, I don't know, for some reason, I like to write that as a fraction, 1 over 1 plus x squared right here. That's my integrating factor. So far, so good? Yeah, so we know what the integrating factor is, and therefore, again, going back to our method here, now we're ready to write down sort of how that proceeds to the solution. So we obtain, what is that looking like? It's the integrating factor, 1 over 1 plus x squared, times my unknown function, which in this moment is u. It's not y, it's u. So I have my unknown function u, and I'm taking the derivative of that. Okay, and then on the other side of the equal sign, I just put my integrating factor, 1 over 1 plus x squared, times whatever the q of x was. Q of x was actually -x. So actually, let's just write this as -x over 1 plus x squared. There we go. Question? Yeah, please. It is right here. Okay, so the original q of x was just x, but then we put the 1 minus n in front of it, which put the minus here. This is the q of x that's being multiplied by the I. So you have to kind of put a couple things together. Here's the q of x, which was -x being multiplied by the I. You with me?
Yeah.
Okay. Everybody else okay with this? Because I realize there's kind of a few different things going on here. If we're good, then the next thing you have to do, as you remember from the process I explained last week, is integrate both sides, right? So now I'm going to integrate. I'll just write that word there, integrate. When I do an integral of something that was already expressed as a derivative, they undo each other as opposite operations. So you'll get 1 over 1 plus x squared times u without the integral, because you've integrated the derivative. And then on the other side of the equation, we have to do the integral. So this is what I was saying earlier. You actually have to do 2 integrals on this method. So we have a minus x over 1 plus x squared that has to be integrated. And is it okay if I squeeze this into the corner over here? Okay, this integral actually is not much different than the one we did a few minutes ago. The only difference is there's no factor of 2 in it. So if you just take the antiderivative that we got before, which was -ln of 1 plus x squared, and just put a 1/2 in front, you'll get the right answer. So this is going to be -1/2 of the ln of the quantity 1 plus x squared. Again, by basically a u substitution. However, in this case, unlike when I solved for the integrating factor, in this case, guys, we do need a plus c on that. Okay, because now we are trying to come up with the general solution to the differential equation. So you're gonna have a C in your answer. You have to. Right. Okay, I need a little more room, so I think I'm gonna come over here and finish it. We're almost done. Almost done. What do you suppose I should do next, guys?
Even both sides,
One more time?
just even both sides together in the logarithm.
We could, but I would do something else first. Do something else. It's a good thought.
Move the one over and one x squared.
Yeah, I kind of want to get u solved for. I'd like to get u figured out. So to get u by itself, guys, everybody can see this. To get u by itself, I'm going to take this 1 plus x squared and throw it to the other side of the equal sign. And let me write that down over here just because I have more room. Let's write down what that's going to look like. What will happen is, okay, so just follow me on this. I'm going to take the 1 over 1 plus x squared and I'm going to flip it to the other side. And then I'll be left with the quantity of -1/2 the ln of 1 plus x squared plus c. And use those brackets, guys. Those are your friend. Parentheses, brackets, braces, whatever you want to call them. What I don't want to see, and having taught the class 40 times, I sort of know what the issues tend to be. And one of them is that some people will just leave that plus c dangling on the end all by itself as like an extra term that in this case should not be by itself. This c really is being multiplied by the 1 plus x squared. And mathematically, that's different than just having a plus c dangling off the end. Right, so use those brackets to make sure you don't get mixed up with that. All right, are we done?
No,
What am I still needing to do?
back to you.
Switch back to you guys. My original problem does not have u in it anywhere. It's all about x's and y's. My final solution should be for y. And that's why I had us write this change of variables down early on, right? The relationship how to go between the u and the y is going to come from this. And so you see that they're reciprocals of each other. So if I know what u is, then I can get, as a final step, I can get what y is. Y is simply 1 over all of that. So I just recopied everything of what u was, but now it's in the denominator. Sweet. And that would be a final answer. Now, if I gave you an initial value, like if I told you what y of 0 is, and I gave you some number for that, then you'd be able to solve for c as well. And that would give you a what's called a particular solution. But this is the general solution, which is all we can do here. We don't have any more information to go any further. All right. People with me here a little bit? Great. So that's one of the two. I'm going to do two examples. That's one of the two illustrations of change of variables. We take a Bernoulli differential equation, which is right here. We implement this change of variables right here to convert it into this linear differential equation here. And then we solve from there. We solve from there. Yeah, exactly. Okay, so far so good, hopefully. Questions? All right. Good. I hope I'm making sense. I don't teach in the summer, so I always come back in the fall. I'm like, oh, yeah, I hope I still know how to teach this stuff. You know, when you've done it 40 times, it's pretty well hardwired now. I actually haven't been here that long. It's just I have literally taught this class like every semester. I love it. The other professors don't want to teach it. And I think it's because when the first time you prep this course, it was a lot of work, right? It's really a lot of work. And so everybody else has kind of figured out what they want to do and they don't want to deal with this. So they just hand it to me again. And I'm more than happy to take it off their hands. Yeah, okay, let's talk about the second one, and then as I said, we'll take a 10-minute break, but I'd like to do part B here before we get to that. So part B, I am gonna again start off with a definition this is just gonna be another example of how we can change variables to turn a differential equation that we don't know how to solve, namely the homogeneous ones, into separable ones. In this case, it turns out it becomes separable. So let's write it down. A first order differential equation is homogeneous of degree 0 if it has the form Okay, so what's the form? Well, the first thing is to really identify that it's homogeneous of degree 0. You need to get the y prime isolated on one side of the equal sign, the first derivative of y. And what this should be equal to, of course, the other side of the equation is going to have your x's and your y's in it. I don't know exactly what it looks like, but it's some function, which I'm going to write as f of x and y on the right-hand side. So a homogeneous differential equation should have this form where the derivative of y is equal to some mishmash expression involving x's and y's. But it can't just be any old thing on the right-hand side, because if it was, then every equation would be homogeneous. So there must be some condition about this f that really dictates that it's homogeneous of degree 0. So I'm not done yet, right? I have to add what that condition is, and I'm gonna do it right now. It's kind of a quirky little thing, so we'll write it down and then we'll practice it on a couple of examples before we get too deep into it. But there's this little trick that you have to use. And what it is if you take this function f, excuse me, and everywhere you see an x, you change it to xt. And everywhere you see a y, you change it to yt. Okay, so I'm going to go all through the right-hand side of my function, of my differential equation. And I'm going to change all the x's to xt. I'm going to change all of the y's to yt. I'm going to look at that, right? And if it happens to be the lucky miracle case where all of those t's cancel back out again and leave me with the original function, then it's homogeneous of degree 0. Okay. So that's the definition, and it looks a little bizarre, so we're gonna try an example or two here just to make sure everybody's good with it. So let's just play with an example. Maybe we'll do a couple examples of this just to make sure that this is clear. Let's suppose that I gave you a function f of x and y. So I'm not explaining how to solve this differential equation yet. What I'm doing right now is just making sure we understand what this little condition here means. So it'll be a moment and then I'll explain the change of variables. Let's say we had x divided by y minus 5. Let's say that's what showed up on the right-hand side of your differential equation, right? So what I'm going to say, guys, is that this is not homogeneous of degree 0. I'd like to make sure you're convinced of that. If I take my function and I replace all of my x's and y's with xt and yt, what does it become? Well, on the numerator where I had an x, now it's xt. In the denominator where I had a y, it's yt. And so we get this expression xt all over yt minus 5. The question is that equal? That's this question here. Is that equal to what we started with? What do you guys think? Are these equal? Not in any algebra world that I know. Definitely not, right? You would have to be able to cancel the t's, but I hope everybody knows that we cannot just cancel these two t's because there is a 5 over here that does not have a t with it at all, right? So it's not balanced, in other words. So yeah, this does not work. It's not homogeneous of degree 0 in this case. let's try another one just to make sure. Is everybody clear with that? Again, I get excited, so if I'm going too fast, you just have to slow me down. Let's do one more example. Let's say we had f of x and y. And this time, let's say what we had was y squared over x squared plus 3xy. Yeah, this time I claim that this one is homogeneous of degree 0. And again, you wouldn't necessarily know that just looking at it. You have to write this out, but I'm basically going to tell you what's going to happen. So if we look at f of xt and yt again, we do kind of that same trick again. So I go back to my function, and everywhere I see an x or a y, I replace with xt or yt. So in this case, the numerator becomes yt quantity squared. And then the denominator becomes xt quantity squared plus 3 xt and yt. The question that we have to pause and think about now is, looking at this, would it be the case that all of those t's would cancel back out and leave me with what I started with? And you might notice here that, see, if you think about it, in the numerator, you have a t squared with a y squared on it. But in the denominator, if you factor a t squared again, yeah, you're going to get x squared plus 3xy. And look at that. I can cancel those t squareds completely and leave myself with exactly what we had started with. Okay, do we kind of see the difference here? Actually, you know what it really comes down to is, if you imagine that every single x has a weight of 1 and every single y has a weight of 1, those x's and y's, they get weighted by the t's. And in this second example, every single term has a weight of 2. There's 2 y's on top. Here I have 2 x's and I have 1 of each. And so those t's pile up the same weight on the top and on the bottom. They can totally cancel it out. Whereas in the one in the numerator, it doesn't work, or the one on the top, it doesn't work. I've got 1 t on top here, there's 1 t here, but there's no t's here. It's not balanced in a way that you can factor and cancel those t's out. It's something you kind of get used to when you've done 3 or 4 of these. Make sense? So far, my friends, I have not explained at all how you solve these differential equations. I've just been trying to understand what this homogeneous of degree 0 means. Yes.
What does degree 0?
That is a good question. So you're gonna get the gold star points for asking the good questions. We're not going to worry about degree 1, degree 2, or degree 3, but just so you know, I could think of this as f of xt and yt is equal to f of x and y times t to the power of 0. And that 0 is the 0 we're talking about. So if you wanted to know, what does it mean to be homogeneous of degree 17? Well, that would be that you ended up getting the original function back with 17 extra t's attached onto the end of it. Okay, real good question. But we are only going to worry about t to the 0, which we don't even have to write down. Okay, great question. So the issue now becomes, how do you solve these? And again, somebody way smarter than me and way before me figured out what kind of a change of variables we could use to solve one of these guys right here. Okay, so let's write it down. So to solve these types of differential equations, the homogeneous of degree 0 ones, what we're going to do is we're going to use a change of variables, but not the same one we used for the Bernoulli equations. And so I'm not even going to use the same letter for it. I'm going to use a different letter just so we don't get them mixed up too badly. I'm gonna call it V, and here's the change of variables that some genius way before my time figured out that we can use, namely V equals Y over X. Now, actually, in point of fact, when you look at the differential equation, it starts off with X's and Y's in it. What you're going to be doing is changing the Y's into V's. So it's actually more useful not to think of it this way, but rather the way you'll actually use it in practice is with it solved for Y. So I'll rewrite it. It's the same equation. It's basically just a mathematical rewriting of it. Y equals X V, and that's X times V, right? X times V. And so if I know that that's what Y is, then I also can write down what Y prime is. Oh, why do I want to do that? Well, because my differential equation has Y prime in it. I'm going to need to replace that in terms of V. So what is Y prime? Well, if I just use the product rule here, guys, first term times the derivative of the second plus the second term times the derivative of the first, here is Y prime. X V prime plus V times X prime, but X prime is just one. So there you go. There's Y, there's Y prime. You substitute those in and bingo, it becomes a separable differential equation. Let's do a quick example to see that, and then I think we're going to be done with chapter 1. By the way, this is the last section in chapter 1 that we're going to do. The rest of it, you'll have to take. Well, I'm sure you're all going to switch to math majors. Once you become math majors, the rest of the stuff about numerical differential equations and so on, that'll all get covered in your 300 level math classes, but we won't bother with that here. Okay, let's try this example, guys. Let's solve Y prime equals, somewhere in equals, don't I? Yep, equals Y over X plus the square root of 16x squared minus y squared, excuse me, all over x. Okay. You know, one of the things we can get inadvertently lulled into in this chapter is a problem that you probably also saw when you took second semester calculus, which is that, do you remember second semester calculus where you learned all the integration techniques? And so for one section, all of the problems were done with U substitution. And then in the next section, they were all integration by parts. And then the next section, they were all partial fractions decomposition. You sort of got trained. Oh, if I'm in this section, here's how I'm going to do it. And if I'm in that section, here's how I'm going to do that. We can fall into that trap here as well. I should not be looking at this differential equation and just jumping to say it's homogeneous, even though that's what we're talking about. I should really get in the habit of asking myself, well, is it separable? Oh, maybe it's already separable. Maybe it's linear. Well, we just learned about Bernoulli equations. Maybe it's Bernoulli, right? So we should really get in the habit, and we're going to practice this on Thursday in groups at the whiteboards. I'm going to have you guys practicing, just identify, is it separable? Is it linear? Is it Bernoulli? Is it homogeneous? This is 4 types of equations that we have pretty much learned at this point. So when I look at something like this, I really shouldn't just, jump to the, it is homogeneous. Obviously, that's what I'm trying to practice with you right now. But we shouldn't just assume that. I should ask myself, would it be possible to separate this? Well, not in any algebra world that I know. Right? I see a square root that has a minus sign underneath of it. There's no way in the world to separate the x and the y that are underneath this radical, because they're basically glued together by that minus sign. Right? So this is not separable. Okay, at least I'm pretty convinced it's not. Remember, there's always the potential that if you do some algebra, maybe you could finagle it into being separable, but it sure doesn't look easy from here, right? It's definitely not linear, because when I see a y squared in my equation, I remember the form of a linear differential equation. There's no y squared in that form, right? Can't be that. Bernoulli, you can have a y squared in a Bernoulli equation, but remember, it has to be multiplied out on the end by itself. It shouldn't be buried under a radical like this. So I'm looking at this thinking, it's not looking separable, it's not looking linear, it's not looking Bernoulli. I haven't maybe fully investigated all of those possibilities, but my gut feeling tells me this is probably homogeneous. And we can check that. Let's start our solution here. We can check that if I identify this right-hand side as f of x and y, then when I go through here and attach x's, if I attach the t's to all the x's and all the y's like I was doing a few minutes ago, let's just look at what happens, guys. I get yt divided by xt. So I'm taking this right-hand side and I'm replacing the x's with xt and the y's with yt. And then on the second term, well, the denominator was x, so now I'm going to write it as xt. And in the numerator, I have the square root of 16 times the quantity xt squared minus the quantity yt squared. Right. And the question is, do all of the t's cancel back out again, like they did in this example here on the bottom? Well, let me get out. Is this blue? Yeah, I'm kind of colorblind actually, so this is the blue. Okay, so I'm going to take this blue marker and cancel the t's right there. Okay, and then over here I see a t squared. I'm going to do this kind of quickly. I see a t squared and a t squared, which I could factor and pull out of the radical and cancel with the t that's on the bottom. So I can kind of cancel the t squared from inside the radical with the t that's underneath. And so I do actually get back to the original f of x and y. I'll be a little bit brief about that, but that's how it works out. That is going to work out. Okay, so it's homogeneous. Great. So in that case, if we believe that, I'm going to go back to this equation now, guys, and I'm going to do my change of variables. On the left side, I had y prime. So now I'm going to do the change of variables. Let's just go ahead and write that down. On the left side, I had y prime, but y prime becomes x v prime plus v. Okay, so I'm just putting this box on the left side. That's just the derivative of y in terms of v. And then on the right side, what do I have? I have y over x. Well, that was just equal to v. And then plus, I have this fraction that has the square root of 16x squared minus, now y squared could be written again as x squared v squared. So I'm getting rid of all of the y's and putting it entirely in terms of x's and v's. All right. Give myself just a little more room here and then we'll be good to go. Guys, again, you probably can see that we can simplify this a little bit. I think. So here I have a v on the left and a v on the right. Let's just get rid of those. That's pretty easy. And then not only that, inside of this radical, I have an x squared in both terms. Okay, I'm going to do this kind of quickly because it's just algebra. I'm going to factor that x squared. And in the meanwhile, I'll pull it out of the radical and then cancel it with the one on the bottom. So what that's going to turn into is x v prime equals, when I cancel the x squared from the numerator terms and use that to cancel with the denominator, it leaves me only with the square root of 16 minus v squared. Yeah, okay. Now, let's keep in mind, these are equations that are supposed to become separable. Now, when you're thinking about separable equations, you might remember from my videos last week that I don't like to use the prime notation for derivatives so much. I like to rewrite it using like dy over dx, or in this case, dv over dx, just because that identifies the variables a little more explicitly. The right-hand side is the square root of 16 minus v squared. And does that look separable? Meaning, can I get all of the x's onto one side and all of the v's onto the other side? I better, otherwise I've been lying to you for the last 20 minutes, right? These are always supposed to become separable. Yeah, this is going to be separable. What I'm gonna do, guys, is I'm gonna throw the radical 16 minus v squared under the dv. And I'm gonna throw the dx over x to the other side. So just flip things around a little bit. Should come out like that. And once you get it separated, we have to integrate on both sides. Throw those integral signs there. The right-hand side is a pretty much a standard one. It's just the ln of absolute absolute x. And I have to add my plus c on the end of that, like I always do. When you get to the left side, you might be freaking out a little bit. I just got done telling you, I think that I want you to know how to do U substitutions, maybe once in a while an integration by parts. Well, this is neither of those. This is actually going to take a trig substitution. And I really am not planning to go there much. Like, I'm not going to ask you guys to know those kind of things cold, but this one would appear in some kind of a table. I would give you a table of integrals. And this one, I'm just going to tell you what it is. Don't worry about it, because it's not one that you should be able to do necessarily off the top of your head. Turns out to be the arc sine of the quantity of v over 4. So that's, just take my word for that. Just take my word for that. Don't worry about that part. It's not the key point of 250b. My question for you, though, is, am I done now?
No.
No, what am I not done with? Or what should I still need to do? Change the variable back. I need to change the variable back. I don't want my final answer to have v in it, because the original problem was in terms of x and y, right? So my final answer should be in terms of x and y. So the first thing I might think about doing here is changing that v back into y over x. So I'm going to go ahead and do that inside of those parentheses. The v becomes y over x. I'll leave the right-hand side exactly the same, like so. Okay, I might need just a smidge more room. So far makes sense? Now am I done? If you've got that recap cheat sheet that we wrote down at the beginning of class, in the method for separable differential equations, what it said was integrate both sides and solve for y if possible. Right? So that's my question. Is it possible to solve this for y? In other words, to get y by itself? Think we could do that? I'd have to clear all the other clutter out of the way. So I'd have to get rid of the arc sine, have to deal with the 4x. I think I could do it though. Because after all, the arc sine function is an inverse of the sine function. So if I just hit both sides of this equation with sine, I'll cancel that arc sine from the left side. Let's write it down. It's exactly what you want to do, right? So what'll happen is you'll get whatever it is, y over 4x, I guess, right? Equals, and it'll just be the sine of everything that was on the other side. ln absolute x plus c. And again, use those brackets to make it very clear. This c is not dangling off the end by itself. It's inside those parentheses. Totally required. Right? And I'm still not quite done, but I'm almost there. I just want to get y by itself, so I'll go ahead and multiply across by 4x. So I'll get 4x times the sine of the quantity of the ln of absolute x plus c. And it's not a bad idea to box our answer, just so it's easy for people to find it and check it out. All right, what do you guys think? Is that all clear? Any questions here? Yeah, please.
It's been a while since I've done a trig sub. Do you need a domain restriction?
Let's see. You technically do. I mean, we really needed one from the beginning here, because you can't take the square root of a negative number. So you're going to have certain
right.
x's and y's that don't even make sense here. Whenever you see a problem like this, where there might be some potential, also you don't want x to be 0. right? When you see some potential for there to be illegal values of X or Y, it's always just assumed when it says solve the equation, that you're solving it for whatever domain it makes sense for.
Gotcha.
So yeah, so that would be probably. Good question. Any other questions so far? Okay, if not, before we take our little break, remember, we're gonna take a break here in a minute. I would like to just quickly run through my roster. I think, did everybody get a chance to check their name off on here? I'm just gonna go through and do the best I can. I'm not gonna learn everybody's names in the next 2 minutes, but I'm gonna try to get started and also to just see where we're at in terms of numbers as well. That'll be helpful for me. So let me just run through really quick. Just let me know where you're at, Gabriel. Gabriel here. Thank you, Gabriel. How about Eric? Thanks, Eric. You're the one I talked to the other day from the truck stop in Nevada. Is Robin here somewhere? Thanks, Robin. Yasmin? Thank you. There's no Alex Escobar here, right? Don't have Alex here. Okay, great. Fatima? Thank you. Dylan? There he is. Kevin Fonseca? Thanks, Kevin. Helena? There she is. Thanks. Arlene? Gotcha. Caitlin? Thanks. Amin? Gotcha. Joe? Thank you. Sukman? Perfect. And Andrew Lee? Thanks, Andrew. Where is Brody? Right here. Oh, perfect. Brody. And how about Chris? Thanks, Chris. Janelle? Thank you. Okay, I assume we don't have Isabel. Oh, Isabel, she told me she wasn't gonna be here. Okay, got it. Okay, Catherine. Thanks, Catherine. And how about Josh Navarro? Thanks, Josh. Leon. Gotcha. And there's no Seth here, correct? So, okay. Diego. Here. Thanks, Diego. Quentin. Perfect, thank you. Roman. Thanks. And Armand. Perfect. Keon. There he is. Kathleen. Great, thanks. Hien Tran. Not here. Hamza. Thanks, Hamza. How about Kevin? Kevin's here. And how about Alyssa? Thanks, Alyssa. And Yolanda. Great. And Abdullah. Thank you so much. And then where is Andrew Sanchez? Gotcha, Andrew. And how about Joel? Okay. Thank you, guys. Appreciate it. There were about 3 or 4 people gone and about 2 people on the waiting list. If that holds up, it's looking pretty favorable to be able to add you guys. I probably won't do it today. For those of you trying to add, we just need to make sure that that is done by the beginning of next week. And the way it'll work is I'll send an email to the math department office. At some point, I will have to get your campus-wide ID numbers, but I'll do that later. And I'm pretty confident that it should be okay, hopefully. We have enough chairs, that's what most important thing. Okay, and oh, just a quick reminder, because somebody in my first class asked me about quizzes. I would love to give quizzes. I think they would really be good for having you guys have a chance to assess how you're doing before you take an actual exam. And I've even had my students tell me that in their student evaluations in the past. They would say things like, oh, we should have quizzes, which I always thought was odd. But that was the comment that I generally got. And I would love to do it. My problem is it just takes up too much class time. And so I just don't feel like doing that. So I found a compromise. I found a way to sort of make it a win-win for everybody, force everybody to study a little bit so you see how you're doing and so on. And that is that prior to each midterm, about a week before each midterm, I'm going to give out a take-home quiz that you take home. And it's going to be optional and it's going to be worth extra credits towards the midterm. So it won't be worth a lot of points. It'll be worth like maybe 3 or 4 extra points, but every point counts. So you'll have that opportunity as long as, there's always a catch. As long as you stop by my office just to introduce yourself. You can do it in Zoom. You can do it in person. But sometime, I think I put a date on the syllabus. It needs to be by the middle of September. So you have a couple of weeks, doesn't have to be immediately. But it helps me actually learn your names better if I have a chance to sort of talk one-on-one. And I love part of what I love about the job is actually getting to know the people I'm working with. So I like to just have a quick little 5-minute thing, just a casual thing. You don't have to have a question. You just stop by either in Zoom or in person. And I am writing down who's coming in. There've been a few people already who've done that. So I'd like to just encourage everybody to do that. That's really the way I'm gonna learn all of these names, because I have almost 100 students between my 3 classes. It's gonna take me a little bit of time. So I would appreciate it if you do that, but I think that will be a win-win for everybody. Okay? Guys, let's do this. I never promise exactly when we're gonna take our break. It just depends on when I get to a good stopping point, but now is that time. Let's take 10 minutes. If you wanna go get some water, run around the building 10 times, whatever you need to kind of stretch your legs. This is a great time to do it. And in 10 minutes, we'll start. Oh, and if you have questions on the homework, you can throw them on the sideboard over there. And then we'll come back in 10 minutes and continue. Okay. Louise, can I ask you for a favor? Just erase all the words. Thank you so much.
Yeah. Okay. Are you sure it was time? Like a second. Yeah, it's like second, just like one very this one. Where'd you?
And that's for.
We moved to them. Yeah, we have one. Something. It was the same. Okay. From the cloud at one. Our flower is on the same. Yeah, there's one. There's Torrance. West, north, south.
Oh, really?
Again, they can make.
I do want to make sure you get them down. Thank you, Louise. Do you have a pencil? Would you just add, you can just take this back with you and just let it out? Okay. Add your name to the bottom. Okay, thank you so much. So you heard what I said about it.
Because this is like one of the last two classes I need to get before
I will try.
graduate.
No promises yet, but I'm gonna try.
Yeah. I think number two is shorter. One number two is shorter. Oh, yeah. Have we started? Yeah. Oh. Yeah. Oh, yeah. Yeah, no, I guess a lot. You start paying. Yeah, I know. Yeah, yeah. Look at this.
Well, not
All right, guys, I think it's been about 10 minutes. I hope I've got my timing right. I'd like to get started back up again. During the break, a couple of the problems that are on tonight's homework assignment showed up on my whiteboard. Now, I don't promise to always have time to go over all the questions you guys would have. What are you gonna do if you have questions and we don't get a chance to cover it during class? Come to my office hours, exactly. So I'll have a lot of office hours later to help you, but especially if I think there's a couple of questions that maybe a lot of people might have questions about, I'm usually gonna try my best to be able to work with you on them. So number 6 from section 1.4 was thrown up here. And what you can see here is we have this differential equation to solve, dy over dx. And the right-hand side is 2x times y minus 1 all over x squared plus 3. Now, we kind of can cheat here because we know what section of the book this is from, right? And this is the section where we studied the separable differential equations. So we have a big hint just in knowing that. Probably the way to solve this problem is to get it separated. Now, I'm also, the other thing is I might try to just give hints, but then I get so excited, I usually will give the whole thing away. We'll see if I can restrain myself on some of these problems. But this one, I would definitely, it looks promising, doesn't it, that we could separate it? Yeah, so if we did that, what would end up on the left side? Not natural log n, I just want to do the separating part. dy over y minus 1, that's what I was looking for, right? Everything involving y goes on the left side, yeah? And then on the right side, I have to throw this dx over there, and everything else is already on the right side. So we have 2x over x squared plus 3 dx. Okay, and now you're just going to integrate on both sides. That's the method for this. What's the antiderivative of y minus 1? Natural log of technically the absolute value of y minus 1. And then on the right side, this looks like a u substitution, right? It's just du over u. And so this just becomes the ln of x squared plus 3. I will put a plus c there on that side. And notice I did use parentheses rather than absolute values, only because x squared plus 3 is already positive. It really doesn't matter if you use absolute value there or not. Would this be my final answer? No, we would want to do what? Exponentiate on both sides, exactly, because we actually want to try to explicitly solve for y, right? And if I exponentiate on both sides, then the ln and the e cancel on the left side. So I get absolute of y minus 1. And on the other side, well, we have to remember that e to the ln cancels to x squared plus 3, but then there's an e to the c here, which actually technically gets multiplied by that expression. And it's really just a new constant. I'll call it c1. So you saw me doing this in the videos as well, where I would relabel, like I've added e to the c. I can just call that c1. Okay, still not done. I need to remove those absolute value bars, which costs me a plus or minus, right? If I tell you that the absolute value of x is 5, then that means x itself is plus or minus 5. So you have a plus or minus that would go in there. And plus or minus is really just another constant. So I'm going to change the C1 to C2. What you call the constants is kind of up to you. Doesn't really matter that much, but don't keep calling them the same C all the way through. They really technically should be changing as you go along. And now you're pretty much there. You just have to add 1 to get y by itself. So 1 plus C2 times the quantity x squared plus 3. And that would be a final answer. Seem okay? A lot of it's just algebra and a little bit of integration as well, but not a whole lot more than that. Okay, in this same section, there was a word problem about Newton's law of cooling application. And basically it's a Sherlock Holmes mystery. The air temperature outside was 34 degrees. And Sherlock Holmes discovers there's a murder that happened. And at 2 p.m., the victim's body temperature had dropped to 38 degrees. An hour later, it had dropped to 36 degrees. And really, just to make a long story short, the question is asking, what's the time of death? What was the time of death? The time of death would have been normal body temperature. I think it assumed is 98 degrees. So you're basically trying to figure out when was the object 98 degrees given these other values, okay? So guys, this problem is literally just a numbers plug-in game. It's not actually solving any differential equations here. You can just use the result of solving Newton's law of cooling, which was in my video. So the temperature at time t is, T sub m plus C2 e to the negative KT. The T sub m, that's 34. That's the temperature of the medium, which is the surrounding air. So that would have been 34. And then you have to solve for C2 and for K by using the other information here. Now, one thing you will have to decide is at what time is T equals 0? When are you starting your clock? And actually, there is no right or wrong answer to that. You can choose any time that you want. But if you want the numbers to just be a little bit nicer and easier, I'm going to suggest that we let the time be 0, and I'm going to suggest we do this in hours at 2 p.m. Again, you don't have to do that. You could just 3 p.m., you could just 4 p.m., you could just 5 p.m. It really doesn't matter. It will work no matter what. But just for numerical simplicity, it's kind of nice to already know that T of 0, the temperature at time 2 p.m., was 38 degrees. I like to be able to just plug that number in. Okay. And then 1 hour later would be 3 p.m. and the temperature was down to 36 degrees. So these are 2 pieces of information that will allow you to now solve for these 2 unknowns, the K and the C2. By the way, I was saying earlier, I'm not much of a calculator guy. I'm pretty theoretical and conceptual about things, but this is an exception to that. It would be perfectly okay to grab a calculator and use that to help you solve for these constants. Now, once you solve for these constants, what you'll want to do is you'll have the final expression. You'll need to put in 98 over here on the left side of the equation and see what time it is. Solve for the little t. And again, a calculator might be helpful there. So in this case, I am going to restrain myself and let you fill in some of the details there. There's nothing about calculus here. It's literally just plugging numbers in. It's just an algebra thing. So that's how you do it. If anybody needs more of the details of that, let's do that part in office hours. This at least gets it set up for you. And I hope that that will be at least a good starting point. Okay. This one did not show up on my sideboard, but in my morning class it did, and it seemed like it was really useful to show people this problem. So even if you, and by the way, even if you haven't done the problem yet, it's okay. You can still take some notes and try to help yourself out here. This is from section 1.6, and that was about linear differential equations. Let me remind you that a linear differential equation, this was already up on the board earlier today, but it looks like this form right here. Y prime plus P of X times Y equals Q of X. So what do you suppose the first thing is that you're going to need to do in order to solve this?
Divide 2 cosine square x.
Exactly, guys, you have to have the Y prime alone, no coefficient in front of it. So the very first thing I would do, let's start the solution here. The very first thing you're going to want to do on this problem, my friends, is to divide it through by 2 cosine squared of x. So I'll go ahead and do that here. All of that times y. And then on the right side, 4 cosine to the 4th of x all over 2 cosine squared of x. So that's exactly how we would simplify that. Now, on the right side of this, we can clean this up quickly, right? The 4 and the 2 comes out to 2. And then I have 4 powers of cosine on the top, only 2 powers on the bottom. That leaves me with 2 powers on top, and there's nothing left on the bottom. So just cleaning up the right side, it's just 2 cosine squared of x. Okay. And then the other thing I wanted to tell you here, guys, is that, and again, I'm not a big stickler about obscure trig identities. You won't see a lot of this, but here we do have a sine of 2x. And there is a trig identity for that, which is, I'm gonna put it in the top here, 2 sine x cosine x. Okay, so you'll need to do that. And then in the denominator, we have 2 cosine squared of x still on the bottom. This is helpful because then we can cancel quite nicely. The 2's cancel. One of these cosines cancels with one of the ones on top. Okay. And so what am I left with then? I have y prime plus, what's sine over cosine? Tangent, right? So plus tangent of x times y equals 2 cosine squared of x. So this is really the beginning of the solution. You need to get kind of the trig identity taken care of and get it into the right form where now you have a p of x and a q of x. And I'm gonna let you take it from here to find the integrating factor. Now, guys, the integrating factor, I guess here I go. I just can't help myself. The integrating factor is, e to the integral of p of x dx. So you do have to do the integral of tangent. This one will be in your table of integrals, but you can also do it by a u substitution if you wanted to. It turns out to be negative the ln of the absolute value of the cosine of x, and you don't need a plus c on that. So just in case you want to check your work later, but this one you would not have to know cold. I'll give you a formula sheet with that on it. And now to cancel the e and the ln, you have to put a negative, this negative sign as an exponent. Cosine of x, when you reciprocate it and take a -1 power of that, cosine turns into secant. So this problem scares people a little bit because of some of the trig that's in it. But the process, the 250B part of it is kind of just standard process. So anyway, I really try to stop. If you get stuck on that, you've got 8 more hours to figure it out, 3 of which I'll be in my office at least. So there's going to be a chance to get more help if you need it. People feel okay? All right, I'm going to leave it at that as far as the homework for tonight goes. There is an assignment due at the end of the week as well on Friday. This is not that unusual for 250B, so be ready for it. Most weeks there will be a couple of assignments, but on Thursday, as long as you have gotten started on that assignment, which is based on the Bernoulli and homogeneous differential equations, if you get started on it, I can help you with it on Thursday in class. So be sure to try to get a look at that before that. Okay. Well, guys, I said earlier, we could just keep going. One type of differential equation after another, after another, after another. I could just spend 15 weeks just like hammering you with all of these different types of differential equations. But at the end of the day, that isn't going to feel terribly satisfying. You will have memorized a bunch of stuff, but will you really feel like you are equipped with the mathematics you need to really tackle real world problems? I kind of doubt it. There is something much more powerful that we can do at this moment in time. And that is actually to say, look, we got a little bit of our feet wet with differential equations here, but we're going to set them down for a while. And we're going to develop an entire theoretical apparatus for ourselves, which is the whole subject of linear algebra. That is an entire branch of mathematics that we can later in the semester. By the way, guys, one of the reasons I love teaching this class is that the best part of it is at the end. When we come back to these differential equations again later, and we find out that this 9 or 10 week hiatus into linear algebra that we're about to begin can somehow really be transformative in our ability to take lots of types of differential equations and figure out how to solve them. But we need those tools. So that's what we're gonna do. It's not the way my university did it when I was a student. I sat through my linear algebra class the whole semester thinking, oh, what is this good for? I have no idea. This is all so theoretical. Where's the fun, the application? And it was hard to see it. And then I sat through my differential equations course and I was like, why is the professor, he hasn't even done a differential equation for a month now. What's going on? Well, it turned out he had to fill in all these gaps of the other subject that he hadn't taught at that point. And so he was a great professor. He was a great professor, but it was just the way the curriculum was set up was not maximizing sort of the potential for these two subjects to interact and to sort of feed off of each other. And that's what I like about this class, is the ability to do that. But we're gonna set this differential equations down for a while. Now, of course, I'm gonna be bringing up examples to try to keep it in the spotlight when I can, but we're gonna use linear algebra. We're gonna learn some linear algebra that will ultimately be, by somewhere around November, it's gonna be like a highlight of the semester to see that material that we're gonna learn now come back full circle and help us to solve many more differential equations than we can in this moment. And it won't feel like memorizing stuff. It'll feel like, wow, we've really equipped ourselves to like have a totally new perspective on solving these problems. So I really like that about this. I hope you will too. Time will tell. We'll find out somewhere around November. We do have to start kind of slow. I'm gonna just get about a 12-minute start here today on chapter 2. And this is mostly going to be kind of some background material. A lot of you might already know some of this stuff, but it doesn't hurt to just make sure that we are kind of all on the same page. So this is called matrices and systems of equations. Okay, so I'm going to at least get a little bit of a jump into this, and then of course on Thursday we'll pick this back up again. So I apologize in advance. There's going to be quite a few definitions just to kind of get this off the ground. So bear with me, but I'm just going to define what I mean by a linear equation. Okay, and you all have seen these before, so this is not any big earth-shattering definition, but a linear equation. Notice I'm not saying differential equation. We're setting that down for now, right? A linear equation has the form a1 times x1 plus a2 times x2 and then plus dot 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 plus an times xn, and this is equal to b. Right, and so in this context, these a's have i's and the b, those are constants. And the xi's, those are the unknowns in our linear equation. Okay. So this is an equation and it's got some unknowns in it and it's got some constants. That's basically what I'm saying. And then just to follow that up before I do an example, a follow-up definition would just be that a collection of these linear equations, right? A collection of linear equations is called a linear system. It's a linear system. A collection of linear equations is called a linear system. Let me just write, just for the benefit of having something to look at that we can kind of see an example of. And then this is like totally different than what we were talking about the first half of today's class, right? There's no differential equations here. There's just these linear equations. So I've got a couple here to write down for you. Negative 3x plus 2y plus c minus w equals 5. That's a linear equation. And then maybe we also have another one, 2x plus 2z equals 3. And let's write down one more, negative y plus 5z plus 2w equals 0. So there you see an example of a system of linear equations, or in other words, a linear system. A collection of equations. Now, when you have a system of equations like this, guys, what is our main goal? This is going to be one of the primary things we're going to do in chapter 2. One of the main goals here is to solve linear systems for the unknowns. So that's a typical type of question that we're going to have in this class. So I'd like to take this equation and solve what is x, what is y, what is z, what is w. Those are the unknowns, which are playing the roles of the x1, x2, x3, and x4 from the original definition. That's the goal, solve for the unknowns. Now, I can tell you with another example, this will become very obvious to everybody in the room, I'm quite sure, that if I gave you this linear system, x plus y equals 1, and x plus y equals 2, okay, that is a linear system of equations that has the unknowns x and y, but I think you probably would all agree that there's no solution here. It is impossible to solve for x and y. I'm going to come back over to my goal here and be a little more conservative, and I'm going to add the words if possible, okay? If possible. So this is not always going to be possible, but if it's possible, then we would like to try to solve for the unknowns. So this one doesn't have any solutions, and so that leads to another definition, guys, which I will jot down here next. So another definition, a linear system. Again, sorry for bombarding you with all of these terminology so quickly here, but this is pretty basic background information. A linear system with at least one solution is called consistent. If there's a solution, at least one, there could be several, but if there's at least one solution to your to finding the values of your unknowns, we're going to call it consistent. Otherwise, okay, no surprise here. Otherwise, it is inconsistent. Okay, so every linear system is either consistent or inconsistent, depending on whether it has any solutions or not. So let's go back to this example that I just wrote down above here. I just want to add the little comment here that this one is clearly inconsistent. Right? Inconsistent. Any questions so far? Is everybody with me? Mathematicians are often on the receiving end of some jokes. The jokes come from engineers and physicists and things like that. And the joke is something along the lines of that the mathematician actually doesn't actually solve the problem at all. They just want to know, they're just going to wake up and tell you whether you can solve it or not. The building is burning down, right? There's a huge fire, and the mathematician wakes up and says, yes, there's a solution to dealing with this fire, and then goes back to bed. It's kind of a funny thing. And you are going to notice that in this material, that there will be many times when I actually soften this goal, and instead of actually needing to solve it, I just want to know, can I solve it? Yes or no, and that's all that we'll care about. This will become much more prevalent in chapter 4 when we get a little bit later into the semester. Certainly in chapter 2, we're going to try our best to really try to solve these systems. Okay, well, I have just a couple minutes, and I'm just going to throw one more thing at you here, and then we will be done for the day. And that is just simply, how are we going to attack this goal? The title of this chapter, I've already addressed a little bit of it, systems of equations, but there's another word here. And it's the word matrix, or the plural being matrices. Some of you are probably familiar with these, but in order to approach this goal, we're going to take our linear system and put it into a matrix form. So we will use matrices. We will use matrices to solve linear systems. That's going to be our approach, and therefore I kind of need to spend, I guess, 2 minutes, whatever I have here, not a lot of time, but I need to at least tell you what a matrix is, and then maybe write down a quick example. Okay, we won't get too deep into it right now. So there's always a size associated with a matrix, M by N. This little X is usually pronounced with by. So an M by N matrix, and we usually use letters, capital letters from the start of the alphabet. It's pretty typical for matrices, so I'll use a capital A in this case. Capital A, capital B, capital C, those are typically the letters we will use for matrices. And what is this? This is an array of numbers or functions. And these will have been arranged into M rows and N columns. So it's kind of in some kind of a block shape, right? With, it's got rows and columns, almost like a spreadsheet that you would see on one of your online software programs. So you got rows and columns, and it's just arranged like that. So just as a quick example, again, I'm not going to get too much further into this, but I'll just write down one example here and maybe a quick follow-up comment. So here's a matrix, capital A. The first row is -3, 2, 1, and -1. The second row is 2 and 0 and 2 and 0. And the third row is 0 and -1 and 5 and 2. And I just have a question for you guys about this. What would be the size of this matrix? The M by N numbers. 3 rows, right, by 4 columns. The rows go horizontally. There's 3 of those, and then 4 vertical columns. Sometimes you'll see me just write it over here next to the matrix, kind of circle it just so I can see it real easily. Something like that. Can somebody tell me where I got these numbers for this matrix from? If I go back to the example over here, do you see the first equation? -3, 2, 1, -1. Those are exactly the numbers in the first row of this matrix here. Second row, 2, 0, 2, 0. Same thing. So this is actually going to have a name, and we're going to call this, I'm going to have you write this down real quick too, the matrix of coefficients for the linear system. For the linear system above. And so that's where it's coming from. So that's what we're going to be doing, guys. We're going to be taking our linear system and then writing down a matrix to go with it. One last thing, and then I promise I'm done. Sorry, one last thing. This matrix, right, you might have noticed it is ignoring the numbers on the right-hand side, but we will usually want to keep track of those too. So there is something that allows us to do that, which is called the augmented matrix. This is the last thing for today. An augmented matrix. I'm going to call that A with a £sign next to it. This sort of highlights that we're emphasizing that it's an augmented matrix. And this one is just the exact same matrix, guys, but with one extra column added on to the right. And we actually want to use a bar here. You'll see that this is very important to put a bar before that right-hand side column. But that's basically what the augmented matrix for the system would be. Here, we're keeping track of the numbers on the right-hand side. So we're gonna take our linear system. We're gonna put it into this augmented matrix. And then we're all gonna come back on Thursday so that I can show you how we then take this augmented matrix and accomplish the goal of solving the system for the unknowns. Let's do it next time. I'm done for today, guys. Thank you for being here, and I will see you soon, either in office hours or on Thursday. Great.